maybe we can actually start. First of all, welcome again to the colloquium, Heidelberg Joint Astronomical Colloquium, especially today, thanks to all of those who have turned up from all the dispersed institutes, despite the bus strike that we have at the moment. So today we have one of the pioneers of our knowledge of massive stars and their properties, and in fact stars of all kinds, which many of us use in daily work, and we're very privileged that you're able to visit us and tell us about your latest work. And I'm going to hand over to Sylvia's host, Andreas, to do the formal laudatio.
Thank you, Richard. Yeah, it's a pleasure to have Sylvia Ekstro here. Actually, I think Sylvia has one of the more unorthodox careers in our field, because from 1988 to 1999, Sylvia actually was a midwife in a Swiss hospital, in the regional hospital. And she talked so much about science with her husband that one day her husband said, well, you should actually study that and not just talk about it. And so that's what she did. So she studied from 1999 to 2004 physics at the University of Geneva, then did her master thesis on rotating population 3 stars with Professor André Médère. Then stayed on for a PhD on the evolution of fast rotating massive stars at low or zero metallicity with Georges Ménet. And since then, she's a staff researcher at the University of Geneva with a 50% science and a 50% head of communication position. So you're also doing a lot of outreach. She's probably best known for her involvement in the Stellar Evolution Code GENEC, which stands for Geneva Evolution Code, which she has reorganized, optimized, and upgraded in 2013 and is also maintaining ever since. She has had many responsibilities in the scientific community. Most notably, she's been a panel member for the European Astro Roadmap 2022 to 2035. And since 2021, she's also an elected member and the secretary of the organizing committee of the IAU G2 division on massive stars. Sylvia has also won a few awards, just to name. In 2008, she got the Planter-Moore Previous Prize of the Faculty of Science at the University of Geneva for her paper on evolution towards the critical limit and the origin of BE stars. And recently, she has won the Leadership Award of the EU Business School. So with all of that introduction, we are looking very much forward to hear more about your work. And Sylvia, take it away.
Do you hear me? Do you hear me well? Yeah, I think it's on. Yeah. So thanks a lot for this invitation. I'm very honored to be in front of such an audience. I will drive you through stellar evolution in the theoretical part of it. Mostly, you have very eminent observers and specialists of observation. So I will really dive into the core of massive stars. If I can, yeah. So the first question is, of course, why bother about massive stars at all? They are very, very rare objects. Actually, the IMF is absolutely not favoring it. Only 2 to 3 massive stars are born when 1,000 of other masses stars are born. So they are not favored by the IMF, and they are on top of that very short-lived. So they are really very rare objects. But they are extremely important objects. They are actually at the heart of every astrophysical topics. They are very key players for the chemical evolution of the universe. Actually, they are probably the first source of metals for the universe. And they went on producing a lot of metals, very important ones. They might have been the hard photon source for the reionization of the universe. At least they have probably largely contributed to reionization. When we look at distant galaxies, what we see is mainly massive stars. Even if they are rare, they dominate the spectra. They can be used as standard candles in the first and second rung of the distance ladder of the universe, either as the higher luminosity Cepheids or as B supergiants. There has been some proposition to use them as standard candles. They have very, very strong radiative and mechanical feedback, so they shape the interstellar medium. And they also regulate star formation, triggering it by mechanical feedback, but also preventing planet formation or preventing star formation through the UV radiation. But we don't know them really well, because they are so rare that most of our knowledge is based on models. And for a long time, observations were very, very scarce, and so we could not really constrain the models. We had some physical insights, but we couldn't check it really well. Now, since the last decades or two decades, we have surveys that start increasing their numbers. So we have passed from a few hundreds to a few thousands. And of course, now we start seeing discrepancies between the models and the observations. So we start having constraints, and we need to address them. For example, we have a challenge towards the predicted populations. We see, for example, I don't know, do you see my mouse? Yes, you see my mouse. So we have overdensities in the population that are observed, which are not predicted by models. For example, here you see that the terminal age main sequence finishes here, and we have a lot of stars over there, or terminus, depending on the models. You have also a larger main sequence, but still you have overdensities that are not explained by the models. I think with the mouse it's fine, because it can be seen online. Thank you. We have challenged to the chemical feedback that they bring. We see now very luminous galaxies at very high redshift, so already early times. We see that there is large populations of massive stars in them. And with the spectroscopy that the James Webb Telescope is bringing, we can reveal the abundances of these very early galaxies. And we see that we need very high abundances, high nitrogen abundance, for example. And we need now to explain that, because standard model cannot explain exactly that. It's a kind of a puzzle. With gravitational waves, we have also challenges about their structure and evolution. Normally, the theory says that stars with core masses between 65 to 130 solar mass are supposed to explode as parent stability supernovae. So you expect no remnant at all, so no black hole. And so we expect a mass gap in the gravitational waves progenitors. But then when you see this plot of the masses of the black holes that the gravitational waves observe, we should not see anything in this region. So there are some output of the merger, that's fine, but we see that there are some progenitors also here. For example, here we have a progenitors, here we have progenitors. So we see that we have stars in this mass gap, in this theoretical mass gap. So we need now to explain that. So the ideal would be to have full 3D modeling of massive stars, and that would be it. We would start from first principle models, and that would be perfect. Unfortunately, we cannot do that. Full 3D modeling is out of reach, and I will explain you why. If you want to follow the largest to the smallest scales in a turbulent gas medium, then you need to have a ratio of that relates the Reynolds numbers to the power of 3/4. And typically in stellar convective zones, you have a flow speed over the viscosity, which is 10 to the 8, which means that you need 10 to the 6 grid points in every direction to really solve all the scales correctly, which means 10 to the 18 cells in the computation domain. So now we have very large state-of-the-art hydro simulations with 1,536 to the cube cells. And when we want to cover, for example, 1,000 seconds of the evolution, we need 10 million CPU hours. So a small back of the envelope computation, and you know that simulating a full star during the full life, and let's say that we have a huge computer that we can, expand our computation on 1,000 billion CPUs, this would require, I'll let you compute, 10 giga-years, okay, of computations. So details, I hope I convinced you, we can't do full 3D hydro, so we are bound to model stars with 1D codes. And of course, 1D codes are less precise. We need some recipes to cover some of the process that we want to model. And I will take you through the stellar modeling. How do we do that? So we first start with the 4 basic equations of stellar structures. We have the mass conservation and the hydrostatic equilibrium that already tells you how your star is structured and layered. And then you need to follow the energy conservation and the radiative transfer through the star. And so you see that you need, of course, the energy rate and also the opacity to do that. And for this, we have tables that are kindly provided by big facilities of atomic physics, and for example, at CERN or at Fermilab or at Los Alamos. And so we have these tables that we put in the computation. Then we need an equation of state to follow everything. The most basic form of an equation of state relates the density to pressure to a given power, and the temperature to also a given power. And in stars, we usually need an equation of stars that is a mixture of gas and radiation. Actually, Lord Eddington in 1926 already had made a little calculation. If I take a sphere of gas with gas and radiation, how much of the pressure is due to radiation and how much is due to pressure? And you see that for our sun, it's mainly gas pressure. To almost 90% of the pressure of the sun is gas pressure. But for massive stars, we go to 60% or even 85%. So it's really, radiation becomes very important for massive stars. Now, an important, very important ingredient of the modeling is convection. You have a very strong energy generation in the core and the burning shells. And then also sometimes you have cool phases. So you don't have really energy generation, but you have a large opacity. So you have convective zones inside your star in the burning shells. And then also sometimes in the outer convective zones, you need also to cover the convection. Convection, of course, is turbulent, and you need multi-D normally. So how do we do in our little 1D codes? So we try to make a cow spherical, more or less. And what we see is that when we try to make a cow spherical, everything that makes the cow is what is not spherical. So it's very complicated to have convection in a 1D code. So we want to do that. We need first to define which zone is convective or not. And with the linear perturbation theory, we can show that the stratified medium is unstable depending if you take the gradient of chemical species or not. But you need to have your nabla rad larger than your nabla ad. And so you can say, okay, this layer should be convective, or this layer can be radiative. Of course, you need to do that very carefully from inside the convective zones to find the border of the convective zone. Step 2 is to decide which thermal gradient you will use inside your convective zone. In deep interior, it's quite easy. We can consider convection to be adiabatic and instantaneous, so it's very easy. But near the surface, we need a way to compute the thermal gradient. What is usually done is to use the MLT, which is a very old prescription of the 1958, where you consider that your convection flow, it's just one cell, it's cells of a fixed size that move for a fixed distance, which is this little L of the MLT, before it is dissolved in the star. And so you have a free parameter, which is your alpha MLT, and then the pressure scale height. There exist quite a lot of more sophisticated prescriptions, but that are difficult to insert into 1D codes. But you can try and play with it if you wish. But usually most codes just use MLT. It's way easier and computationally also faster. Does it work if we use only the definition of the boundary, the boundary of convection? Actually, we see that no, if we just use the boundary of convection as described by Schwarzschild-Ledoux, we see that we cannot reproduce the width of the main sequence, for example, or data that is given by binary stars or asteroseismic measurements. We are too short. We see that, okay, convection is fine. We see where the acceleration of convection is, stops, but obviously something happens at the border of the core that needs to be taken into account. What is happening is that your convective movements doesn't stop where the acceleration stops. You still have some velocity, so you expect your cells to go further away than the moment where the convection is not an acceleration anymore. We call that overshoot. You might hear that a lot in the stellar evolution community. We are always talking about overshoot, how we model it, why we model it, how big it should be. So we artificially increase the size of the convective zone. And then we can see that depending on how much we put, we can better accommodate the observations, either with a moderate overshoot for the low mass stars or a higher overshoot for the higher mass stars. We see that we need something, and it has been also confirmed by 3D models of convection that show that indeed the flow overshoots the zone where the acceleration stops. Now we need to calibrate this overshoot. It's like a free parameter in the models, and we need to calibrate it. And here, of course, we need exquisite data if we want to do so, exquisite observational data. And also what appears is that depending on with what kind of data we calibrate it, we get different results. When we calibrate it on low mass stars, we get a rather low overshooting parameters. When we calibrate it on 16 solar mass stars, like Ines Brott did for her grids, she gets a higher overshoot parameters. So is it mass dependent? Is it just the stars that were used that were special? This is a question still. When we calibrate it on binaries also, it seems that this favors high overshoot parameters. But of course, overshoot is what you put on top of your core. So depending on the physics you have in your models, your overshoot parameters will be different. When asteroseismology gives us an overshoot parameter, it gives us what they needed to add on top of their model to get to the asteroseismic measurement. And so if you don't have the same physics, if you don't have the same resolution, you might not need the same overshoot parameter to get the same results. So the physics of the models is very important. You should need to test every physics for getting what overshoot these physics needs. Now, what has been observed is, of course, convection brings the matter at the surface, the processed matter at the surface of the star when you are in the red supergiant regime. You know, you have a deep convective zones that dredges up what the hydrogen burning core has been producing. But observation very early showed that this was not sufficient. We had nitrogen enrichments already way before. During the main sequence, we have nitrogen that appears at the surface. So we need a mixing in the radiative zones, not only the convective ones. And of course, one easy culprit that has been identified is rotation. When you have rotation, you triggered some instabilities that mixes in that brings mixing in the radiative zones. So what are the effects of rotations? First, it deforms the star. You have a support by the centrifugal force to the gravity, and this deformation, so the support is larger at the equator than at the pole, so you have a deformation. You have a modification of the gravity that is not the same everywhere in the star. It becomes latitude dependent, okay? Because you have a balance between the centrifugal force and the gravitational acceleration. And so the net effective gravity that the star will feel is no more constant on the full surface. You see the deformation can reach 3/3 of the polar one. The equatorial radius can become up to 3/2 of the polar one. So if the gravity is latitude dependent, so is the TF. And so depending on the rotation rate, you will have a cooler equator and a hotter poles. This is very important because, first of all, you see that this effect is really visible for fast rotators only, but it appears already, you have already a little imbalance, thermal imbalance between equator and poles already for lower rotation rates. So you have definitely that the flux and the TF will depend on the viewing angle that you have on a rotating star. If you look at a star that is rotating and you look at it from the equator or from the pole, you will deduce a very different flux for this star and a different temperature. So you need to correct your output if you know the inclination angle and the rotation rate. So this complicates a bit the comparison with observations when you have rotating stars. Also, this very slight difference or very strong difference depending on the rotation rate, but as soon as you have a little difference of temperature between the equator and the pole, you cannot have both hydrostatic equilibrium and thermal equilibrium. So this will trigger a very large-scale movement, which is called the meridional circulation, that was already identified by Lord Eddington again in 25. And this meridional circulation will, mix your star and will transport angular momentum and chemicals. The meridional circulation is not a diffusion by definition. It has nothing to do with erasing an omega gradient. And on the contrary, it can actually build a gradient because it is not a diffusion. It is not triggered by the gradient. So when you implement the rotational effects, you need additional processes to your 4 equations of your star. You need also to transport angular momentum and chemicals. And for this, you need to define the advective term of the meridional circulation and the diffusion term, which is due mainly to the shear. As soon as you have a gradient of omega, you will have a shear between the layers rotating at different velocities. And this will create a diffusion. And also, you can have convection that will be also like a diffusion. And so you have a more complicated equation. For the chemical species, even though the meridional circulation can go in the other way around, it can go the other way than the chemical gradient, it still acts like a diffusion, because if you just take some low metallicity part, not enriched part of the star into a more enriched star, it's like you diffuse a bit your enriched part. Okay, so you can really consider that on the chemical species, meridional circulation is very easy. It works like a diffusion. But for angular momentum, it's very different. Now, what do we see when we implement those things in a star? So you see that first, on the ZAMs, it's really the hydrostatic effects that acts first, of course. The star feels a lower mass. It behaves like a lower mass star with a lower TF, lower luminosity. And when you increase the rotation rate, you really decrease the ZAMs point. But then during the evolution, you have the mixing that starts playing a role. And so it gets a higher luminosity than a non-rotating or a slower rotating part. And you see a real difference between the slowly rotating ones and the faster rotation. But then you see that when the rotation becomes really fast, hydrostatic effects come back. And you have not only the mixing, but you have also the hydrostatic that come back. And the turn off here point is lower for a very fast rotator than for average rotator. Now, of course, the mixing, I talked about rotation, but there is not only rotation can trigger a lot of different instabilities. And it's very important to see what ingredient you have in your models, because it can change the way your angular momentum is transported, so the shape of your omega profile, and it will also change the history, the way your enrichment appears at the surface. Typically here, I just computed the same star. I think it was, well, don't even remember what kind of star. I think it was a 15 solar mass star. Sorry, and I computed it with the advector diffusive, purely hydro effects of rotation, with magnetic fields or with magnetorotational instability. And you see that the profile of omega is quite different. You have here the surface of your star, the center, and you see that at the middle of the main sequence, the magnetic field is almost solid body rotation for your star. And then advector diffusive is the more differential rotation that you can have. And MRI, it's in the middle. But when you look at the surface of your star, the evolution of the nitrogen at the surface of the star, this is a kind of evolutionary axis, since it's the hydrogen center, the hydrogen at the center of the star. You see that the mixing occurs very differently. You have a strong mixing, or you have a mixing that arrives way later in the evolution, and the amplitude is different. So both the moment the nitrogen arrives at the surface and its amplitude is different, just depending on the physics you used in the models. So there is not just rotating models. Okay, there are rotation and rotation. You need to really define what physics did I use for these rotating models. You might have heard of the Hunter plots and the debate about rotational mixing. Does rotational mixing work? Is it fine to consider that rotation can mix the things? And there was this result by Hunter that only 60% or 50% of the stars were correctly predicting the enrichment in nitrogen. There was quite a lot of fast rotators that were not enriched, or slow rotators that were enriched. And so there was this debate, maybe rotation mixing is wrong. Actually, again, it depends on the physics. If you use different physics, here you have a magnetic model, here you have two different advector diffusive models, purely hydro, but with different prescriptions for the shear and the horizontal turbulence, and some ingredients of the advector diffusive model. Here you predict only 50% indeed of the stars, while the two others predict 80 to 90% of the stars. So when you say, is rotational mixing working, you have to precise what kind of rotational mixing, what ingredients did you use. It is we calculate a dynamo. Yeah. Now, of course, what you will see at the surface, and especially for massive stars, is actually the result of an interplay between the wind and the transport of angular momentum. The mass loss will remove mass, of course, but it removes also angular momentum. And then the transport will more or less efficiently bring the angular momentum back at the surface, because you have the core that contracts because of the burning, so it accelerates. And if you have the way to transport this to the surface, you can accelerate more or less your surface. And here it's exactly what I show. I show the surface velocity for different masses, star of different masses. Two of them were computed with just the plain conservation of angular momentum, no transport at all. It's just each layer keeps its own angular momentum and evolves through time, while the other ones were computed with the hydro model, so advector diffusive transport, which is not a very strong one. But still, you can see the difference for 3 solar mass, for example. When you have purely conservation of angular momentum, since the star is expanding, you have a drop of the surface of the velocity at the surface. While when you have some transport, even if it's not a strong one, you can maintain your rotational velocity more or less constant up to quite the end of the main sequence. However, what you see is that for a 20 solar mass, it starts losing some angular momentum. The transport starts not to be enough to really keep the star at the same velocity. And for a 60 solar mass, it's even dramatically decreasing. This one is not angular momentum conservation. It is really advector diffusive, but the transport is not strong enough to replenish the surface with angular momentum because of the winds. So the result is complex. You really need models to decide how the velocity of your star will evolve. And again, had I computed a magnetic 60 solar mass, magnetic fields really couples very strongly the core and the envelope. And so I would have kept the velocity constant. So again, what kind of rotation are you using? The problem with winds is that for 1D stellar evolution, we don't know really how to implement them, or we need prescriptions. We cannot just say, okay, with the conditions of my star, it should lose, it does not come from the star itself. I need to tell it, okay, if you are here in the HR diagram with that kind of luminosity, temperature, mass, and whatever, and gravity, you will lose that kind of mass. We have many prescriptions on the market. Some are empirical, some are theoretical, some are a mix of both. And they exist for different evolutionary stage. And normally we truncate our stars and we say, okay, during the main sequence, OB stars recipes, and then we switch to the red supergiant recipes or the Wolf-Rayet recipes. And so we switch from one mass loss to the other. And you see that we have a lot of choice, even for one evolutionary stage. You can see here the Vink mass loss, which is very much used. It used to be used just as is. And then now we have observations that tell us that probably it's too high a mass loss rate. We need to reduce it. And so, for example, in MESA, now the default in MESA is 1/3 of Vink. So Vink mass loss rates, but cut by a factor of 3, arbitrarily cut by a factor of 3. We have now more recent mass loss rates that take into account the clumping of the wind, which is one of the reasons why we suppose that Vink's mass loss rate is too high. And so we have these different prescriptions that we need to test, because of course, if you reduce the mass loss, you reduce many things, you change many things in the evolution of your star. For the red supergiant recipes, it's even worse. We have really a lot of them, extremely different ones. You can see the Van Loon 2005, which is specifically for very dusty red supergiants. And so they are extremely strong mass loss rates. And if you are not a dusty supergiant, you might completely evaporate. And you have on the opposite side, Beezer and Davis mass loss rates of 2020, which is extremely weak. And so which one are we supposed to use? That's an eternal question for stellar evolutionists. And the Wolf-Rayet recipes also, we have a lot of them here. And again, in which conditions, specific conditions, do we have a discrimination between the different ones? Do we need to use one or the other depending on the star we are considering? This is a very complicated question. Do we have observational constraints? For example, for the red supergiant mass loss, there is a big debate. Do stellar evolution models always overpredict the mass loss rates? This was one of the results of Beezer and Davis in 2018. They measured the mass loss rates in a cluster. So for a quite specific range of masses, and they integrated. They considered the lifetime of these stars in the red supergiant phase, and they computed how much mass they should have lost or they should lose during this red supergiant phase when they were above that mass. And then they looked at all different grades of models to see whether we were right or wrong. And actually it shows that all models overpredict the instantaneous mass loss rate of red supergiant. Now I really insist, instantaneous mass loss rates. Don't forget that when you plug that into a model, you have huge time steps in your models. So if your mass loss is not steadily low, in models, you will need to implement something that is higher, because you will need to implement also the burst that you might have. And when we try to constrain, do we really overpredict them? So this is a bit a complicated plot, but I will try to drive you through it. So we have plotted the percentage of high luminosity red supergiant. The idea behind this is if you have a strong mass loss, the higher metallicity stars will not be red supergiant anymore. They will go back to the blue if you lose mass, enough mass. And so you will truncate your higher luminosity end of this red supergiant. And so in a luminosity function, you will look how much high luminosity red supergiant do I have. It will be lower if you have a very strong mass loss rate. And on the contrary, you can have a lot of high luminosity red supergiant if you have a low mass loss rate. And so we take bins of lower limits for the red supergiant. If I take, because we never know for very lower limits when you count all your red supergiant. In the low end, you have the AGBs that can pollute your sample. So you are not really testing red supergiant, but you might not know it. So we tried to see if we change this lower luminosity and we integrate the numbers of red supergiant, the percentage of high luminosity that we have, depending on what we consider the low luminosity, how many do we have? And here you have the results for M31 and M33, and the result for different models of red supergiants with a mass loss that has been arbitrarily cut or multiplied. And so what we see is that the low mass loss rates of Beezer and Davis is quite excluded by this analysis. It's too low, actually, which might, again, hint us towards the necessity to take into account the burst in the red supergiant phase. You cannot also increase the mass loss a lot. It's also as wrong as to decrease it. So probably the mass loss rate that we have in models is not that wrong on the long term of the evolution. Now, what about binaries? We know that 70% of all stars are in binary system, that they might appear as single stars. So it's complicated to discriminate when you observe a set of stars. Are we observing binaries or not? And when we model stars, how are we supposed to model binary interactions? Stellar physics is very complicated already, but when you add binary physics on top of this, it's a nightmare. Binarity brings very different mixing, the tidal mixing, for example, and then you have mass transfer episodes where you will transfer mass and angular momentum on the gainer, while you remove all that from the donor. And then sometimes your star will merge. And so it will be a single star observationally, but it will have had a different evolution, and maybe it will sit somewhere unexpected. In any case, when you want to model binaries, you need to open a very, very large parameter space. Normally, a star, if you know the composition, if you know the mass, if you know the rotation rate, you more or less know how your star will evolve. It's quite simple. However, when you have binaries, you need also the separation and the mass ratio, and this opens a very large parameter space. So what can we do? We can model specific case with very detailed simulations, or we can simplify the physics a lot to broaden the parameter space and explore it very widely, but it is at the expense of the physics. Does it matter? Does binary physics overwhelm the stellar physics or not? Actually, my opinion, it's that physics always matters. Actually, depending on how you transport your angular momentum inside your star, you will change the strength of the tides. So you will indeed change the way your star will synchronize, for example. You will change the amount of mass that can be transferred. Often, you know, when you transfer mass, you transfer angular momentum, so you spin up the donor. And usually what is used is you stop the accretion when the donor is at the critical limit, because it cannot accept more angular momentum. It's already up to the top. And so mass transfer has to stop. But depending on the transport that you have in the interior, you will change the way you can accept mass. You can accept more or less mass. In this work that we have done, it's just an explorative work that has been done, and we prepare a paper about it. If you use the advector diffusive model, or if you use a magnetic model, you can double or reduce by a factor of 2 the amount of mass that you get on your star. And then you can also change completely the way the star looks after the transfer. Now, we are lucky because statistics is coming. Up to now, I told you, you had only a few thousand massive stars to our reach, but we have very large spectroscopic surveys coming, WEAVE and foremost. We had Jacob that already changed the things with a few thousand stars, and with WEAVE and foremost, we will have a few tens of thousand stars. So it will be really change the game. We will start, hopefully, with a huge amount of data. We will probably be able to go from a few outliers to full populations. These stars that seems weird in our little sample, maybe it's a full population and we need to understand it as population. Or maybe it will remain outliers. We don't know, but we will know. Also, we will really need a lot of observations to be able to identify interacting or post-interaction binaries. And we hope that also with the advent of machine learning, maybe we can do that better than now and explore the observations in an unbiased, with an unbiased eye to say, okay, maybe I can see some signatures that are clear. This is an interacting binary or a post-interaction binary. And so we can know how we have to deal when we want to constrain stars and the physics inside our stars. But we need to do the same effort with the theoretical data. And I think that we absolutely need to go beyond the team-specific ingredients that we are now. If you look at the MESA community, they have some team-specific, okay, they will always have magnetic fields most of the time. They will have a given overshoot parameter because that's the default parameters and it's the way they do things. You go to Franek, it's different team-specific ingredients. They have different overshoot. They have different alpha parameters for the MLT. We do these things also. We have our preferred advector diffusive process for rotation. Maybe this is wrong, but okay, we love it. It was complicated to implement it. It was a nightmare to implement it, let's say. And so now we use it. But maybe we should go to something else, and maybe this is wrong. So we really need to now put everything down on the table, I would say, and start to see what comes up. If I put all my physical assumptions and the free parameters at the same level, and I try to vary everything in a very huge grid of models, well, maybe we can see trends, we can see degeneracies, but maybe we can also lift some degeneracies. For example, when you compute models at a lower metallicity, the composition will change, so your different process will act differently. And so maybe we can lift some degeneracy with that. But in any case, I think that we really need to make this effort of reconsidering our favorite parameters and try to once vary everything and see what emerges, what can be really consistent with the observations we have. And also one thing, which is one of the reasons I'm visiting Andreas often, as often as I can, is that we really need to improve comparison. The theoretical models, they provide luminosities, they provide a TF that is, okay, what the result of a very, very crude atmosphere. The way we compute very well the interior of the star, but the atmosphere of the star is a very crude treatment. And so we have a TF that is wrong. Maybe by chance it's not that wrong, but it is not computed the way it should be. And also we have theoretical values. Now, we absolutely need to connect interior models with atmosphere models if we want to progress. Because we need to really provide observables, synthetic observables, to be able to compare apples with apples. Because now we are really comparing apples with bananas. We had done this effort with José Gros 10 years ago. We started a project with him, and we saw that indeed we can say a lot of things. The TF is completely wrong when we really create a spectra on top of our models. We get a more reliable TF that is different from the one that we used to have. And now Joris is doing the same effort here, and indeed we see differences when you plug an atmosphere, a real atmosphere that has a correct stratification on top of the models. So my takeaway for today is that massive stars are really at the heart of astrophysics, but the meaningful comparison have been very lacking up to now. The models come with many free parameters and physical assumptions, and we need to revise that and to revisit our choices, because depending on the choice we make, we have better or worse predictions. And we should always be very aware of what physics we had in the models when we made this prediction. And two rotating models are not the same. And we really need now to make sure that we don't compare apples with bananas by making the effort of plugging atmosphere on top of our interior models. And thank you for your attention, and I'm happy to answer your questions. It is absolutely relevant, and we do so. We have a shear diffusion coefficient that we use. There are several prescriptions for it. There are at least 2 or 3 prescriptions for this, exactly what you say. There is a shear mixing, the 2 layers rotating with a differential rotation, it will mix. And yes, we do implement that in models. We have a choice in the way we implement it. We have, for now, no way to constrain which one is better. But I hope that with the very large surveys, we might be able to say, okay, this prescription is better than that one. It mixes. It brings some chemicals at the surface. It contributes to mixing. Yes, to mixing of angular momentum and chemicals. Indeed, no, it's absolutely relevant.
Okay, so let's open the floor to questions from everybody. And by the way, online audience, please type in if you have a question into the chat, and then I'll pick you up from here via the mic. So more questions. So who is first? Thomas.
Yeah, thank you for a very interesting talk. Massive stars mean different things for different people. So I'm mostly interested in really massive stars, between 50 and 100 solar masses. And you may certainly not get 10,000 in our galaxy, you may get a few. But let's go to even more massive stars at high redshift. So the prediction is that at high redshift, the IMF is tuned to very massive stars up to 600 solar masses. I personally don't believe that because these calculations don't include fragmentation. But my question is, are there actually models for low metallicity for very massive stars?
Yes, there are. There are quite a lot.
And what are the challenges there? Because I think cooling and everything is very different.
Yeah,
So how reliable are the models for 200 solar mass star?
yes, we have models for this. We have models, I think some grids go up to 1,000 models, solar mass. They, of course, they are very, even for you know, for population 3 stars, the question is, would they lose mass? Is the Eddington factor is extremely high. We think that it should not be reasonable that they would not lose mass, but we don't know how to do that. Because as I mentioned, the wind does not come naturally from our models, so we need prescriptions. And for the moment, I don't know, Kela, if you have ideas on which prescription would be the best for a population 3, 200 solar mass, but that is a good question. Population 3 stars are not visible anymore, normally. We hope that maybe with the James Webb, we might see pockets of population 3 stars in very distant galaxies, but we have no idea. For the moment, we have no constraints on population 3 stars. And the problem that for massive stars in general, even when we have constraints, we don't know how to implement the winds. And for those extreme beasts, I think the wind would be, you know, there should be mass loss, and we don't know how to implement that. So normally what they do is just no mass loss at all, or they use a mass loss that is just scaled down a bit. They use a mass loss recipe that exists for maybe the small Magellanic Cloud, for the Magellanic Clouds, more or less. How relevant is it? I cannot tell you, but you can find massive models in the literature.
That's one of you.
No, we did some models, and Mesa also, the mist, I think the mist go quite high, no, to 500, no? Mikali. Yeah, 200 maybe, yeah. Yeah. Yeah, they are difficult to compute because they are very luminous. And so it's complicated to have them. We would need some mass loss to help us compute them, actually, to stabilize them.
Yeah, I also found the talk very interesting. I learned a lot. I'm surprised actually that the overshoot parameter is such a big unknown, given that, I mean, you made a very convincing argument that ab initio is out of the question, but the overshoot would be, I guess, dominated by the largest eddies, which should then be within the possibility of modeling that at least for a few dynamical timescales in a 3D fashion. So
it is.
So why is it then unknown? Because why don't people just simply brute force it in a box, you know, a local box within the star, and then once you know it, you can put it in your 1D models?
So there has been many 3D models of convection. My knowledge is that hydrogen and helium models have too low Mach numbers to be easily modeled in 3D. And so what we have is burning shells in advanced stages. And yes, we have prescriptions from that. We have the entrainment model from Dave Arnett and his team, for example. Michaela, you have something to add, or?
No, no.
I know it's a question for later. Okay. I thought you wanted to react. So yeah, the problem is that for hydrogen and helium, we can't model that because of the Mach numbers. The zone to probe is too large, and they told me, I'm not a specialist, so they told me, no, we can't do that because Mach numbers are too low. And so, okay. They are trying to supersede that. I think Dave Arnett is working on a helium burning core to try to see what happens there. There is a prescription from 3 to 1D from this team which shows an entrainment process. But the problem is, again, we have a very short, a few convective turnover time. Now, how does it really work in a star that evolves and that goes on evolving? You never know. For the moment, the core just grows. But is it reasonable to think that or not? There are 3 parameters in this parameterization from 3 to 1D. So it's a complicated question. I agree with you, it's frustrating. You say, okay, come on, just do that. But it seems to be complicated. There was some hands, but I wondered if it's a reaction to that question, maybe. So if you agree,
Look,
Michaela.
I don't know. Friedrich, do you want to make a comment or something? Yep.
Sorry, but it's relevant for the question.
Yes, so actually in our group, we actually did exactly these simulations that you requested, Case, right? And especially Robert here did this. The problem is actually sort of, as you described, the low Mach numbers, but in addition to this, you also have a timescale problem there because the overshooting region actually establishes an equilibrium between this convective transport and outside the radiative transport. So you actually have the dynamical timescale and the thermal timescale there, and that's very different. So you can actually see how, as you suggest, the eddies would actually sort of enlarge that zone, but at some point you would expect to find an equilibrium there. And establishing this actually requires to do a simulation that also covers the thermal timescale, and that is very difficult, at least for the early burning stages. And this is something that you should ask Robert about. He actually has kind of a solution to that.
Excellent, thank you. So back to Michaela. Sorry,
Okay.
Michaela.
So that's good. So I think, Michaela, you wanted to say something, right?
I'm a passion person. Thank you so much for your inspiring talk. I think very good, especially for the students. I want to come back to the metallicity issue. So without reaching down to the POP3 metallicities, one thing that scares me is that probably about half of the Wolf-Rayet stars in the Small Magellanic Cloud are single stars, and they have always been single stars. So how do you think that a new approach to modeling the stellar atmospheres and the wind mass loss can solve the problem? Do you think there is a problem at all?
I hope that with a more consistent mass loss coming from the atmosphere model, we could find why. Because indeed, with the models, just as we compute them, we have very little mass loss, so we don't reach the Wolf-Rayet phase. Very difficult. Only the most extremely massive stars can reach that. But
All right.
Andreas, maybe you can say something about this. So Richard's
So
right.
that's okay. We got a lot of questions, but I'm going to take 2 more, if I may. First from Andreas.
I will make it very quick, just a comment to that. So the SMC Wolf-Rayet stars, they are really a mystery, but they show us probably that there's something with the wind physics that we need to understand better. So it's not just computing another sequence of models, it's more than that.
Okay, the last word from the audience I give to Thomas.
Yeah, you talked about convection, but I would expect that you also have tons of other hydro instabilities. I mean, we earned some of your hydro instabilities for disks now. So, for instance, I mean, convective overstability, instabilities, I mean, is that not now included in stellar models?
Yes, there are many things that are included, different things. Beyond convection, yes, in radiative zones. It depends a lot, but for now, usually it is really a few models to explore. It has not been incorporated really in grids of models. And so we have a few results with some different instabilities, Heuberg, Soilen, Holberg, the Schubert-Frick one, and the different ones. But usually it's only specific models that have been with a few masses maybe, but not a systematic approach. We had André Meder had tried to define a diffusion coefficient that takes into account all these instabilities, not by adding them, but by looking at their interaction. But we also just made a few models with this. There was some numerical issues, and we didn't really proceed further with that. It's a complicated story. The thing is, yes, you can add things, but is it right to do that? Because probably they have interactions, you know, so we should be careful when we just put them, yeah. More is not always better. I mean, of course, we know that there are a lot of instabilities, but can we just add them in the models? And this is not clear.
Okay, so let's round off the discussion now. And if I may have those
Yes.
overlays at the end. Sylvia, thank you. I'll just make a couple of announcements. The first is just to remind you all that tomorrow is the deadline for everybody here in Heidelberg to give suggestions to the Institute representatives. It's just coming up here about speakers for the summer semester of the Heidelberg Joint Astronomical Colloquium. So please get in touch with one of your Institute representatives and let them know who you want to invite. Next slide of the announcements tonight. So immediately afterwards, Cormac, go and meet up with Cormac at the front here afterwards, and he'll take you with Sylvia for a sort of informal discussion of drinks at Heavyweights. And then afterwards, we're meeting for everybody who wants to at Saigon Sauna, Hauptstrasse. And last slide of announcements, next week, we are going on to planets again. We're happy to have Martin Pessin coming here to tell us all about planetary migration. So thank you again, Sylvia. Let's give Sylvia a great round of applause for such a fantastic talk.
Thank you. Thank you.